Okay, so welcome to London Learning Lean. This week we're very pleased to have all the way from Mexico, Violeta Hernández Palacios, who is an undergraduate at the University of Guanajuato and very active on our Discord. She's an expert at things like game theory and lean, but she's going to tell us today about ordinals. Over to you, Violeta.
All right, so welcome. Today's talk is not quite going to be about an advanced topic. Ordinals are a bit of an undergrad topic, but my goal in this talk is to give like a new perspective on the topic of ordinals, because, well, as far as I'm aware, as far as I've asked, most undergrad courses on ordinals usually talk about them from a very set theoretic perspective, right? So they're usually part of a larger course on like set theory, ordinals, and cardinals, and whatnot. And the tools that are used to talk about ordinals are quite ingrained, particularly with things like the von Neumann construction, which, as we'll see later, doesn't really translate into lean. So that's kind of what I want to focus on this talk today. I want to focus on the differences between how we talk about ordinals in set theory and how we do it in lean. And I want to talk about how we formalize some of the basic notions on ordinals. So, all right, I'm going to start with a bit of introduction just to the concept of ordinals, just like some basic prerequisites in case anyone doesn't remember their set theory course. So the point of ordinals is to describe well-ordered sets. Let us recall that a well-ordered set is a linear order that doesn't have any infinite decreasing sequences. So the typical examples are, for instance, finite linear orders or the natural numbers. And there's wackier stuff, right? Like you can talk about pairs of natural numbers, for instance, those sorts of things. So, oh, and of course, the other important property about well-ordered sets is that they have an induction principle. You can prove a statement about every element in a well-ordered set if you prove that it follows that the statement for a certain element follows from the statement for all previous elements. So well-ordered sets have an order type. This order type is the ordinal that's assigned to the well-ordered set. And the idea is that if two sets have the same order type, then they should be order isomorphic and vice versa. So yeah, essentially ordinals are a way to assign a single value to a given well-ordered set so that any other well-ordered set that looks exactly the same, that's just like a relabeled version of that set, has the same ordinal assigned. And oh yeah, here's some examples, right? Like there's an ordinal for every natural number. There's 0, 1, 2. There's of course omega, which is the first infinite ordinal. It corresponds to the natural numbers. And you can have all sorts of wackier stuff, right? Like you have omega to the omega. You can have omega 1, which is the first uncountable ordinal. It's kind of a zoo out there. So there's a lot of kinds of ordinals. They can get pretty big, as we'll see. And I don't think I should need to motivate why I want to talk about ordinals. I think they're common enough that they can be considered like an important mathematical subject. But even so, they're kind of niche. So I might still go over a few of their uses, right? Ordinals, aside from like set theoretic arguments, they sometimes make a bit of an appearance in some transfinite induction arguments. So there's a bunch of theorems out there. One particular example that I can remember is the theorem about the cardinality of Borel sets. And these results, even if they don't seem to involve ordinals directly, they usually involve some sort of like cardinality constraint, which then makes ordinals a useful tool to prove those statements. And oh yeah, there's also like a lot of arguments on cardinality, and I think cardinality is even easier to like justify, right? And well, other than the fact that ordinals are a thing that we use in math, there's also some reasons why we'd want to formalize ordinals. One of them is that, well, at least for me, my main interest in formalizing ordinals, at least when I started, was the fact that ordinals are a bit of how could we say this? They're kind of a stress test for formal theorem provers, because they have some formal subtleties that even in a set theoretic course that's usually supposed to be like extremely formal, they're usually kind of glossed over or ignored, so to say. You kind of pretend that they aren't there. Particularly, there's the Burali-Forti paradox, which, as we'll see in a moment, implies that there's no such thing as the set of all ordinals, which, if you try to formalize things in terms of sets, this can really throw in a wrench, because it means that things like functions from ordinals or relations in ordinals you suddenly aren't able to define those in the same framework as you were working with everything else. So yeah, they have some formal subtleties, and what I want to talk about today is how Lean manages to avoid these, or at least circumvent them in another way, contrasted to how set theory does it. And yeah, of course, there's also this notion of proper classes, and this basically all ties to the same thing. Ordinals don't form a set, unfortunately. So, all right, now that I've briefly talked about what ordinals are and what they are supposed to do, I'm going to talk briefly about how ordinals are defined in CFC. So again, I'm just kind of establishing some ground rules. And we're just going to talk about the basic stuff, like what is an ordinal, what are the basic operations, relations, and ordinals. And then we're going to move on to Lean, and we're going to talk about how it works there. So yeah, overview. So, all right, CFC. What is CFC? CFC is pretty much the de facto set of axioms for mathematics. I'm not sure what the historical context is. I'm not an expert. I couldn't really tell you the full story of how CFC came to be and why it has been adopted as like this framework that by default you assume everyone is working in. But that's kind of its current status. And the philosophy of CFC is that everything is a set. So yeah, absolutely everything is turtles all the way down. And examples of sets, pretty much any conceivable mathematical object. The number 0 is a set, the number pi is a set, the exponentiation function is a set, any relation is a set, any group is a set. Everything has to be a set. And so if we want to talk about ordinals within CFC, then we have to figure out how to make them sets too. And the de facto way of doing this is via what's known as the von Neumann construction. So recall what we want to do, right? We want to assign like a unique value to a well-ordered set, such that any other well-ordered set that behaves the same or more formally is order isomorphic to it, it has to have the same canonical representative. And well, the way we do this in set theory is we define an ordinal as a set that's well-ordered with respect to the membership relation that also satisfies that every element of it is a subset of it. And so, well, we can look at a few examples, right? There's the empty set, which satisfies both of these properties. We define the zero ordinal as the empty set. There's also the set that contains the empty set, which again is an ordinal. We define it as 1. The set that contains 0 and 1, which we define as the ordinal 2, and so on. We can keep defining an ordinal number for every natural in this manner. And if you've seen the CFC definition for natural numbers, or at least like the canonical definition, it's exactly the same idea, right? Every natural is a set of all naturals that come before it. And well, ordinals go a step further because you also have the naturals themselves, as in the set of the ordinal 0, the ordinal 1, the ordinal 2. That's also an ordinal. And well, there's a lot of other ordinals out there, much larger ordinals, but we're not going to talk about them on this occasion. And it can be proven. I won't really go into the details here because it gets quite technical. And the point of this talk isn't to go into technical details about CFC, it's to go into technical details about liens. So I'm just going to take this as granted. Every wall order is order isomorphic to exactly one ordinal. And this is what we define as the order type of the wall order. And I'm going to write it as type here. There's not really a standard notation for this, but I needed to go with something, right? So, oh, sorry. So now, one of the main problems with dealing with ordinals in CFC is the Burali-Forti paradox, which isn't really, it's really a theorem, right? But it's kind of paradoxical, particularly if you're only starting to get into these sorts of formal concepts in CFC, right? So the statement of the theorem is that there is no set of all ordinals. That is, there is no single set that contains every single ordinal. And the proof is actually quite simple. If you had a set that contained all ordinals, then it would be an ordinal itself. So it would have to be contained in itself, which kind of doesn't work in CFC. And besides, it means that the membership relation is no longer a wall order. So, all right, what does this mean? Like, what are the consequences of this? The obvious consequence is that, well, you suddenly have to start waving your hands a bit when you talk about some of the things that you'd like to do on ordinals, right? Because in CFC, you can define things like functions, relations, all of that. And the way you do it is by essentially taking some set that depends on the set that you want to define your function or relation on. Like if I define a function from naturals to naturals in CFC, then that function has to actually be a set that in some way contains the set of naturals, right? Or that allows you to represent the set of naturals within that framework, right? If you want to define a relation on naturals, then of course you have to be able to talk, you're going to talk about some set that also needs to be able to represent the naturals. The Burali-Forti paradox tells us that you suddenly cannot do this with ordinals. Like if you want to define a function from ordinals to ordinals, then you're in big trouble, because if there's no set of ordinals, then technically there can't be a function from ordinals to ordinals. And there are workarounds for this. Like the easy way out is to just say, of course, they're just classes, right? So in CFC, a class is a bit of an informal concept. There are other axiomatic frameworks for mathematics that do formalize the notion of classes, but in CFC, they're kind of informal. And well, a class is just anything that you can describe that isn't a set, right? You can think of it as a class is something that can be a set, but it can be too large to be a set, but it's still a class. If it can't be a set, we say that it's a proper class. And oh yeah, that allows you to hand-wavily talk about class relations, class functions, and whatnot, right? And as I said, there are like legitimate formal workarounds for this. Like you can say, oh, we're working in this thing called a Grothendieck universe, which basically means that you can do all of set theory within one really big set. then if you want to talk about something that's the size of that set, like too big for that big set that you had, then it isn't a problem because you're still talking sets. You can also be working within inaccessible cardinals, which is pretty much just a restatement of the same idea. You can be working in alternate axiomatic frameworks like Neumann, I don't remember the name. It's NBG, but I don't remember what the letters stand for.
Neumann Bernays Gödel, I think.
Yeah, I think
No
that's
bloody
it.
good. That's what I was told as an undergraduate.
So yeah, you can sidestep all of these issues that ordinals cause. And like in practice, you're never thinking about them, right? Like if you take a course in set theory that isn't overly formal, you'll probably discuss things like ordinal addition, ordinal normal functions, for instance. And a lot of those times, you do discuss them as if they were actual relations, functions on the set of all ordinals, even though there is no set. So yeah, this doesn't really make a difference when you're like working in pencil and paper, but it does raise the question of how are you going to get this to work in a formal theorem prover? And well, we're not going to get to that yet. I'm going to discuss a bit about ordinal arithmetic and CFC first, and then we're going to get to the bottom of that issue. So the really nice thing about von Neumann's construction is that the basic operations on ordinals correspond to basic set theoretic notions. So an ordinal is less than another when it's contained, like one ordinal is contained in the other ordinal as a set. The lesser or equal relation is just the subset relation. You can take maximums and minimums of two ordinals by just taking their union and intersection respectively. You can take their supremum and infimum, which, well, recall from the theory of lattices. These are just the greatest upper bound and the greatest, the supremum is the least upper bound and the infimum is the greatest lower bound. So those turn out to exist in the case of four ordinals, and they correspond to the union of the set of ordinals that you're taking the supremum of and the intersection of the set for the infimum. And you can even define a successor ordinal, which you can prove is the least ordinal greater than another. And it has a really simple definition in terms of just the basic operations of sets. The successor of X is just the set of X, the set X union with the singleton containing X. So in that way, von Neumann's construction is actually kind of nice because it allows you to talk about a lot of the basic things using only very basic concepts. And of course, ordinals turn out to be a class whole order, a class complete lattice, and a class successor order. Here I'm borrowing some terms from MATLAB, like successor order, but well, I think it's kind of clear what I mean by this, right?
I thought a complete lattice had a top.
Well, there's a bit of a subtlety here, right? Because again, since there is no set of all ordinals, it does turn out that any set of ordinals has a supremum. It's just that,
Yes.
well, yeah, there is no set of all ordinals, so
I see.
you can, so yeah, it's kind of a complete lattice by technicality. It's a weird situation. And as we'll see in the lean, it actually isn't a complete lattice because, well, lean sets a bit differently. Yeah, we can say that it's complete for small sets. Though in CFC, small sets are just sets, so yeah. we'll also talk about just the very basic arithmetic operations in ordinals. So again, just to recap, if you have two wall orders, S and T, you can wall order their disjoint union. You basically just take it, you can think of the wall ordering of the disjoint union by as if you kind of just concatenated S and T, right? So you order S and T, you order the disjoint union so that the elements of S and the elements of T retain their relative orders with respect to one another, and such that every element of S is less than every element of T. And well, we can prove it's not too hard. This is a wall order. And you can define the addition of two ordinals as just the order type of this wall order. And this notion of addition has a few properties that may be a bit unexpected, like considering what addition is usually supposed to entail. It's associative, it has a zero element, but it's not commutative. So yeah, it's one of the few examples that I'm aware of where we call a non-commutative operation addition. But well, that's just kind of how it is. And you can very similarly define multiplication. Instead of taking the disjoint union, you take the product of both wall orders. And the natural wall order on that product is the lexicographic order, the one where dictionary order, you might say. And yeah, you can define the multiplication of two ordinals as just the type of that wall order over the product. And again, it has a few of the expected properties of a multiplication operation. It's associative, it has a, sorry, this should have said one element, it has a one element. And it distributes over the left with addition, but it's not commutative and it's not right distributive. So again, there's a bit of weirdness here, but it kind of makes sense why this is called multiplication, right? It's just a wall order on a product of wall orders. So yeah. So anyways, that's just how things are in CFC. This shouldn't be too new. And these are all things that are seen in a basic undergrad course. So what I'm really interested in talking about today is how all of this works in Lean. And to talk about this, we need to first talk about how sets work in Lean, because as it turns out, Lean sets aren't quite the same as CFC sets in a very important way. And CFC sets are a primitive notion. Like, you have all of these axioms of CFC, and they tell you how sets behave, but none of them tell you what a set is. It's kind of like trying to define a point in Euclidean geometry. It's just a thing that you assume exists, and you have a bunch of axioms that tell you what the properties of that thing are. I think there's this famous quote about how you could do Euclidean geometry with I don't remember the exact quote, something about beer and coffee tables.
Sharing chairs or something.
Oh yeah. So sets and CFC are the same thing. They could be chairs for all we know. In Lean, this isn't the case. You can actually define what a set is in Lean. And the way you define it is the set of type. You define the type of sets of type alpha. I should have added type annotation here. Like, this ends up being a type U. And it's just the type of all functions from alpha to prop. And all this makes a bit more sense if we look at how membership is defined. We say that A is contained in a set S when SA. So basically, in Lean, sets are just functions that tell you for every element whether it is in the set or not. That's what sets in Lean are. And this may look a bit innocent, because in most circumstances, like if you're working with alpha, I don't know, the real numbers or the natural numbers, or maybe, I don't know, points in a sphere. Usually this notion of sets does correspond to the one that you have from CFC, right? Like if you're talking about real numbers, you can define some yes or no function on every real number, and then take the set of all real numbers for which they give an output of yes. And in this way, you basically recover the lean definition of sets. But there are a few subtle differences that really start to materialize when we talk about ordinals. So first of all, a set can only contain elements of the same type. This makes a lot of sense if you're working in type theory, but it is a different situation from what you have in CFC, right? In CFC, you don't have any notion of types. You can have a set and you can put whatever other sets you want in there. So yeah, that's going to be relevant quite shortly. And another difference between lean sets and CFC sets is that in lean, every type has a universal set, which is just the set where everything belongs in it. This, again, if you're working with something like the real numbers or whatnot, this isn't really a problem. It's what's expected. But when you start talking about ordinals, well, that's where the subtleties really start to cause trouble, right? Like, let's say that we wanted to formalize von Neumann's construction from earlier in lean. We immediately run into two very big problems. The first problem is that it isn't really well typed. Like, we wanted ordinals to be sets that contain other ordinals, which have to be sets that contain other ordinals, and so on, and so on, and so on. In CFC, this wouldn't be a problem because, again, you can pretty much put whichever set you want into whichever other set, and it's no problem. But if you're working in type theory, well, then it gets pretty messy really quickly. There might be a way to actually get this to work. Like, I don't know, maybe have a sort of some type of sets and sets of sets and whatnot, and maybe define like some weird membership relation in that. But I think it's way more trouble than it's worth. It should be kind of clear that it just gets really messy. And the second problem with trying to define ordinals as these sorts of sets is that suddenly you're subject to Burali-Forti, because if there does exist a set of all ordinals, it's just set that you need. So if you want to define ordinals as sets, then you somehow need to be able to talk about the set of all ordinals without causing paradoxes. And again, there might just be a way for this to work, but it just seems too troublesome. Wouldn't it be nice if there were some other way that could more naturally capture what we actually want to do, which is to give canonical representatives to well-ordered sets? And well, foreshadowing, there actually is, because lean has a tool that pretty much is designed to do that. It's designed to give canonical representatives when you have some sort of equivalent relation on a type, and that's quotient. In fact, quotient is one of the things that is axiomatically defined in lean. Well, not quite axiomatically, but I believe that there are a few constants in an axiom which are related to quotient. So in a completely different way, we're still talking about ordinals from this like relatively basic perspective. Like, we're talking about them from the perspective of the basic axioms of our framework, right? Before it was set theory, and now we're talking about quotients. And well, since this talk is about lean, I might as well elaborate on how quotients work. So let's do this by example. So first, we're going to define a bundled well-ordered structure. So this is our structure, it's called well order. And it's basically just going to be a type with a well-ordered relation. That's all it is. You might notice that the type of the structure is, if it contains a type U, then the type of the well-ordered structure is in type U plus 1. And this is going to be relevant quite shortly. So just to keep in mind. And what we're now going to do is we're going to define a setoid on that well order. Well, what is a setoid? A setoid is pretty much just a bundled equivalence relation. So we're going to define this ordinal that is equivalent relation on well order. And what we're going to do is we're going to say that two well orders are equivalent when there exists an order isomorphism between them, which is what we want, right? We want to give a canonical representative to well orders such that if there is an order isomorphism, then they have the same representative, so to say. And we might as well even look a bit at the code here. This function takes in these two well orders. It breaks them down into their arguments. So we have this first well order with type alpha, relation R, and proof of well orderedness WO. And we have this other well order on type beta, relation S, and proof of well orderedness WO prime. And the reason that we subdivide them into their components is so that we can then easily refer to RNS explicitly. And here it is. We just say that the relation is that the type of all order isomorphisms between R and S is non-empty. In other words, there exists.
Is there one of those R's is not like the other R, right?
Yeah, that's a fair point. This symbol right here, the equivalence R, this is actually just one symbol. Like,
that means order preserving isomorphism.
Yeah, indeed. So
got it.
R equiv RS, I'm not sure how to pronounce this. This is a type of all order isomorphisms between R and S. And well, recall that an order isomorphism is just an equivalence. So a function with a bundled inverse and proof that these are indeed inverses. That's an equivalence, right? And an order isomorphism in Lean is just an equivalence, but you also have a proof that if two elements are related by R on alpha, and then you apply this equivalence, then you get two elements that are related in beta by S. I see someone raise their hand.
Yeah, so but then I see a third R before the lambda. So I realize the definition of the this is still another one.
Yeah, there's a lot of R's in here. So this first R is just it's just a name for one of the fields of the setoid. So like a setoid is supposed to be a relation with a proof that it is an equivalence relation. And R is just the name of the relation, and its equiv, which we're going to get into shortly, is the proof that R is indeed an equivalence relation.
But this is not the same R as the R of alpha. I mean, that's the okay.
No, that's just a field name. It's not even a variable. So
okay, I see. Mm-hmm.
Yeah, I'm glad you bring this up because now that I think about it, there are a lot of R's in this proof. The symbols could have been a bit more clear, but I guess that's just a lot of Lean conventions clashing in one unfortunate circumstance. But yeah, the gist of it is just that two orders are equivalent when there is an order isomorphism. And well, maybe I should just bring this up because I was a bit confused about this at the beginning. Why are we using non-empty instead of exists? And the reason is that this equiv R thing, this is actually like a type. Like R equiv RS is not the proposition that R and S are order isomorphic. It's rather the type of all possible order isomorphisms between R and S. So to say that we want there to exist an order isomorphism, we just say that this type of all the possible order isomorphisms is non-empty. So yeah. And I might briefly go over this is-equiv proof here. I didn't really have a lot of lean proofs in this set of slides because I'm more interested in the approach than the actual proofs here. But this proof is relatively simple, so we might as well just briefly skim it over. To prove that this R right here, this relation that we just defined, is an equivalence relation, we need to build a structure with 3 fields, which are expectedly the proofs of reflexivity, symmetry, and transitivity. To prove reflexivity, we have a wall order with fields alpha, R, and another field that we won't really care about. And we want to find an order isomorphism between this wall order and itself. Unfortunately, there is already one such isomorphism defined in the math of library, which is reliso.refl, the obvious order isomorphism between some relation and itself. So since this exists, that proves reflexivity. To prove symmetry, well, that's relatively simple too. If we have 2 wall orders, which again we just split into their fields for convenience, and we also have a relation, an order isomorphism between the first and the second, then E.sim, this gives the obvious like inverse order isomorphism between S and R. Sorry, between the second and the first. And finally, for transitivity, well, this is also already defined elsewhere in MATLib. If you have an order isomorphism between R and S and another between S and T, then you can build one by just composing them between R and T. So this is the one we provide as evidence that if the type of order isomorphisms between this first and second wall order is non-empty, and the type of order isomorphisms between the second and third wall order is non-empty, then we can build this other order isomorphism between the first and the third. And well, yeah, this proves that the relation that we just defined is indeed an order isomorphism. And with these 2 fields, the relation and the proof of the equivalence relation, we have R seroid. And well, finally, all we need to do is just define the type of ordinals as the quotient of wall order by the previous seroid. And here's how that looks like. And again, note 2 things. The first is that our type of ordinals is universe parametric. It depends on which type of wall orders we're taking, which depends on what the allowed universe is for the types within that wall order. So yeah, ordinal is universe parametric. It depends on this universe U. And the second thing to note is that it ends up being of type U+1 instead of just type U or type 0 or whatnot. And again, this is going to become quite relevant shortly. So let's just briefly look at the basic notions on ordinals and how they translate from CFC to lean. In CFC, we demanded that every ordinal be a well-ordered set under the membership relation. But in lean, ordinals aren't types. They're just like there is a type of all ordinals, but any specific ordinal isn't a type. It's an ordinal. So we need to be a bit more indirect if we want to talk about ordinals being well ordered. And what we do is we define these 4 instances. We first just define this attribute instance on wallorder.wo so that lean is aware that, as a matter of fact, any given wall order the relation coming out from any given wall order is in fact well ordered. So yeah, that's made into an instance so that Lean is aware of that. We then define, and now in order to talk about specific ordinals as well-ordered sets, or rather well orders, what we do is we use this .out function, quotient.out. So what quotient.out does is when you have some quotient on a setoid, it just gives you some element that is equivalent to that. So it gives you like a representative. You can think of a quotient as being like the type theoretic analog of equivalence classes. So quotient.out just gives you an arbitrary representative from set equivalence class. You can really conclude anything about it other than it just belongs to the equivalence class, but it turns out to be convenient as a canonical representative of sorts, because even though the output of quotient.out is pretty much completely arbitrary, it's still going to be the same every time you call quotient.out. So in that sense, it does kind of serve as a canonical representative, and it's what we use in order to talk about specific ordinals as being well-ordered types. So we first define like a canonical well-founded relation for every ordinal on the type we get out of O.out. So recall that O.out is going to give us some well order, our structure well order with capital W, that is equivalent. Well, it's going to give us a representative for the ordinal O. And then by calling .alpha, we get the type of that representative. And well, we do have a canonical well-founded relation that it's just the relation R that's in the structure O.out. And to prove that it's well-founded, well, we just take the proof of well-orderedness and then conclude well-foundedness. It's a bit dense, maybe a bit confusing, but it starts to make sense. Like, the idea here is that you can, in some way, think of O.out.alpha as being like a well-ordered type for O, like the canonical well-ordered type for O. That's kind of the idea. So you can define a linear order. In particular, you can define what the relations less than and less or equal mean. We just define them to match this R relation that we had on our well order. And finally, we can just define this instance that O.out.alpha is well ordered under the less than relation, which the less than relation is just definitionally equal to O.out.r. So to prove that this is a well order, we just need to call O.out.w, which is exactly the proof that O.out.alpha is well ordered under O.out.r. And well, it's also possible to define a more precise equivalence. In fact, this is only an equivalence. It's actually an orderized morphism between the interval of ordinals that are less than O and this type O.out.alpha, which in CFC, this would be like an equivalence, right? This is the way that we would define ordinals. But since we can still get an orderized morphism, it means that we can still talk about, like, we can still kind of talk as an ordinal having the ordinals less than it, just in a more roundabout way. So hopefully that wasn't too confusing. Now, as for order types, this turns out to be quite easier to do in Lean than it is in CFC. So we kind of win some, we lose some, right? We can very simply define the type, the order type of some wall order as just the ordinal corresponding to the wall order. Like, I don't know how else to put this. So these symbols, these double brackets, they essentially build an element of a quotient from an element of the type that's being quotiented. So basically, you can think of them as building the equivalence class, like continuing that analogy, right? And so the order type of a wall order is pretty much just the ordinal that corresponds to its equivalence class under order isomorphism, which makes sense. That's like exactly what we want, right? And to prove that two wall orders have the same order type, if and only if there exists an order isomorphism, this is almost immediate. It's just like a more general property of how quotients are defined. Two quotients are the same. Well, the quotients built from two representatives are the same if and only if the representatives satisfy the equivalence relation. So that's it. We get this pretty much for free. And now let's talk about ordinal arithmetic. So we have talked about how the basic relations in ordinals, like less than, less or equal, maximum, minimum, supremum, infimum, they all correspond to basic set theoretic notions. In Lean, this isn't quite going to be the case, but instead they're going to correspond to basic order theoretic notions, which it's nice in its own way, right? So briefly, before talking about this, we need to just briefly mention lift, quotient at lift. And what quotient at lift does is, well, in normal mathematics and like pencil and paper mathematics, we're used to saying that you usually see people talk about relations defined on equivalence classes. And they'll say, oh, this operation is well defined when the output doesn't depend on which representatives you take from the equivalence class. And well, of course, this is a bit of a language abuse, because what exactly would be a non-well-defined operation? Like, you're supposed to be speaking formally. You can't like not define something formally. But we all kind of understand what we mean by this, right? And luckily in Lean, we can actually formalize this idea of a well-defined operation via quotient.left. What that does is you have a function from some sort alpha to some sort beta. It can be a type or it can be a property. It's really relevant here that it's a sort. I just kind of copied the definition over. And you have some set S, again, bundled equivalence relation that you use to build a quotient. And you also have that for any two elements that are equivalent under this setoid, the output of the function is the same. If you have this, then you're able to lift, quotation marks, that's just how it's called. You're able to lift this operation from alpha to beta to a function from the quotient of S to beta. And well, the way you do this is essentially just, well, the same way that you would talk about defining an operation on equivalence classes normally, right? Like, you just define this as the output of any representative. And well, there's also a lift too for binary operations. So I'm just briefly mentioning this because this is how we're going to define a lot of the operations from ordinals. So yeah, lifting. And let's see some examples of lifting. So first of all, the less or equal relation. This can be quite simply defined as the following way. We Well, we're going to say that a wall order R is less than a wall order S when there exists an order embedding from R to S, which is to say, you can basically embed the order for R in the order for S. Like you can take an injective map that preserves order. We don't require an inverse map here, which is the difference between an order embedding and an order isomorphism. And well, if you look at here at the code, what we actually do is we use quotient that left on 2. So the relation that we have, this is a relation on wall orders, right? And in order to get a relation on ordinals, we need to prove that for any 2 equivalent wall orders, this means order isomorphic wall orders, the fact that one embeds into the other, that still holds, right? So like if there exists an order isomorphism between a wall order A and a wall order B, no, sorry, if there exists an order embedding between a wall order A and a wall order B, and you have C and D that are equivalent, as in order isomorphic, to A and B, then there must also exist a order embedding from C to D. And this isn't too hard to prove, but I did omit a proof here for purposes of time and space. And just as a technical note, this isn't actually the MATLAB definition. Like in MATLAB, you more precisely require an order isomorphism such that the range is left closed. So in other words, the range of this order embedding, if some element is in the range, all lesser elements must be in the range. But this is mostly just for convenience for proving some basic results. And you can prove that this other relation, that the one that I've written down here, is actually equivalent to that one. So yeah, not really a big deal. So we can prove that the type of ordinals is a linear order. The proof is not immediate, but neither is a CFC proof, so that's kind of to be expected. And once you do that, you can recover a maximum and minimum, which is something that's defined for every linear order. And an infimum, you can define it as in a general wall order, as just, well, the minimum, right? Where it gets kind of messy is when we talk about supreme. And, well, we briefly mentioned before how ordinals were only a complete lattice on a sort of technicality. Well, this translates over to Lie. What happens is this. In CFC, every set of ordinals has a supremum. But as we've seen before, it isn't really the case that the ordinals themselves have a supremum. So that's kind of like the technicality. In Lean, however, this cannot be a case because the ordinals, like the set of all ordinals, that has no supremum. You can prove that if it had a supremum, then you could build some other ordinal that's larger than it, and that would be a contradiction. But here's where it gets really interesting. Every type U index family of ordinal.U, I missed some brackets here, does have a supremum. So what this means is that, in a sense, there is a correspondence between these families indexed by type U and the sets that we see in CFC. In fact, this suggests a mental model for how to think about universes in Lean. I don't know about you, but the first time that I learned about how there was type and type 0 and type 1 and whatnot, I got really confused. I thought it was just a really weird technical way to avoid really weird technical paradoxes that wouldn't actually like have any tangible impact. But as it turns out, there is a kind of simple mental model for how these different universes in Lean behave. You can think of type 0 as basically everything that's small enough to be a CFC set. This isn't really a formal description. It's, again, just kind of a mental model. Type 0 is the small things. If you aren't able to define something at type 0, like for instance, type of ordinals over type 0, that has to be in type 1. And what that means is, again, mental model, not really formal. It's a sort of proper class over type 0. It's too big to be in type 0. So we need to treat it in the same way that we treat proper classes in CFC. If you then have something like type 2, then it means that it's too big even for type 1, and so on and so forth. So the fact that every type U index family of ordinals in type U has a supremum, but it kind of suggests, well, the thing that we were saying earlier, small sets have a supremum. That's pretty much what it means. And, oh yeah, since Lean requires that every Lean set, since complete lattices in Lean require that every Lean set, which, as we've seen before, doesn't behave the same way as a CFC set, it requires that every Lean set has a supremum and infimum. So because of the fact that set.unif is a thing, since ordinals don't have a top element, then they don't actually form a complete lattice. They form a slightly weaker structure with quite a mouthful of a name, a conditionally complete lattice with but. I'm not actually sure like who defined this in MathLib, but I'm like 90% sure that this was defined pretty much only for ordinals. So a conditionally complete lattice is a complete lattice such that every bounded set of elements has a supremum. And it turns out that ordinals do satisfy this property, because it turns out that you can index any interval of ordinals using some type from type U. More precisely, you can index the interval from 0 to an ordinal A using a.out.alpha, which is like the representative type for the ordinal A. And since this lives in type U, then we can index this set by type U. And, well, ordinals also have a bottom element, which means that we can deal with infima in a way that's a bit more nicely to the way that we deal with supremums, right? Because, well, you have whole order type, so infimums are just going to be minimums. So that's why we have this more specific structure. So we have this added convenience of all of these theorems about infimums, basically. And just briefly, let's go over addition and multiplication. As you can see, addition is defined pretty much in the obvious way. This is pretty much the same. This is pretty much the Lean translation of the CFC definition that we saw earlier. We just defined the addition of two ordinals as the order type of the wall order on the sum type of the wall orders. So this sum.LXRS, this is pretty much the wall order that we were describing earlier, where every element from alpha comes before every element from beta, and they preserve their relative orderings. And this by exact I sum.LX, that is wall order, this is just something that we have to do in order to inform Lean that indeed this is a wall order. And for ordinal multiplication, it's basically the same thing. We define well, actually, this kind of shows that. Yeah, actually, this shows that I had the CFC definition slightly wrong. The ordinal A times B, it's actually the order type of B times A. That's something I seem to have gotten wrong. Or maybe Linus, yeah, I think I got that wrong. Or maybe Linus uses different convention, not sure. But anyways, as you can see, to take the product of two ordinals, we just need to take representatives for those ordinals and take the whole order on the product of types. And again, here's a proof that this is a whole order. And after this dollar sign should go a proof that this doesn't depend on which representatives for the ordinals we take. Again, I just omitted it because of convenience. And well, that's almost the end of our talk. I just want to briefly mention a few things in a more freestyle manner, just in these last few minutes. It seems like I actually went a bit over. It seems like I actually went a bit over time, which I wasn't expecting. It's my first time doing a talk like this. So I just wanted to briefly mention the thing that we said earlier about how in CFC it was complicated to talk about like functions on ordinals, relations on ordinals. Well, as you can see, on Lean, this is absolutely no issue whatsoever. Because in Lean, you don't have this distinction between like sets and proper classes, where they're fundamentally different objects that need to be dealt with in fundamentally different ways. Instead, you just have types of different universes. So what this means is that you can talk about functions, relations, whatnot, just fine. As long as you have everything in the correct universe, everything just works, which is really nice because, well, first of all, it allows us to define these operations of like less or equal, addition, multiplication. We can actually tangibly define them as operations in their own right, instead of having to argue that, oh, actually, they're just this class thing that we kind of have to informally deal with, right? So, and we don't have this problem, and that's worth pointing out. Another thing that I wanted to briefly point out that I really didn't have the time to discuss this in depth, even though I would have wanted to, is cardinals. So in CFC, you might know that cardinals are usually defined as just specific ordinals, right? Like you define the operations of cardinal, addition, multiplication, and whatnot. You define them differently from the operations of addition and multiplication and ordinals. But it's still convenient to use the von Neumann construction to basically just say, oh yeah, cardinals are the smallest ordinals of a specific size. That's basically what you do. And in Lean, you don't do that. It turns out to be much more convenient to use the same idea of, well, for ordinals, we define them as a quotient of whole orders by order isomorphism. For cardinals, you can do the same, but instead of for order isomorphism, you do it for types and equivalents. So cardinals are really just the quotient of all types in a given universe by the existence of an equivalence, or you might say a bijection between those types. And you can still prove that there is a natural correspondence between ordinals and cardinals, but now it's not definitional, which is not really an issue, but it's another difference from how this is done in CFC. So I think it was worth pointing out. And well, that concludes our talk. And I don't know, what's the protocol here? Any questions, I guess?
Yeah, I now say thank you very much and stop recording. Thank you very much indeed.
Thank you.